Thank you very much, Semra. Thank you for the invitation to your very nice workshop. I'm sorry I'm not able to attend in person. It's not as good, but I'm happy to listen to the talks from my kitchen. So please, if you can't read my handwriting, let me know at once so that I write bigger. So I would like to talk about a recent result with Xi Wang, a colleague from China. It's about the L1 norm for homology classes of complete manifolds and its relation with some geometric invariants. So the L1 norm was defined by Gromov along with the simplicial volume in the 80s. And if you don't know it, for now, think of it as a topological invariant that we hope will give us some geometric information. Although it's a topological invariant, it happens to have strong implication for geometry, and the talk is about some of these implications. So I'll start by defining the L1 norm. So if you take X a topological space, and you choose alpha, some homology class of degree k with R coefficients, then you define the L1 norm of alpha, denoted as this, as the infimum over the L1 norms of all representatives A of the class alpha. So alpha is a homology class, so it's represented by some closed cycles, and over all these cycles, we take the infimum of the L1 norm. And what is the L1 norm? Well, it's if you have this A that can be written, it's a singular cycle, so it can be written as a finite linear combination of singular simplices that represents my class alpha in HKXR. So its L1 norm is simply the sum of the absolute values of its coefficients. Okay, so this is what we call the L1 norm of alpha. So it's among all singular cycles that represent alpha with R coefficients, we take the L1 norm of this representative, meaning the sum of the absolute values of their coefficients, take the infimum, and this is the L1 norm of the class. Actually, it's not a norm, it's just a semi-norm, meaning that some non-zero classes can have zero L1 norm. So this is something that lives in R bigger or equal to 0. And we'll see an example in a minute, but we still call it the L1 norm. And a very important particular case is when X is a manifold. I'll denote it by M, N for its dimension, and I'll always suppose it's oriented in this talk, closed and connected. I'll write OCC in the following, oriented closed connected manifold. Then there is one particular L1 norm we are interested in. It's the, maybe let me give some details. So an oriented closed connected manifold has an important class called the fundamental class. It's the generator, one of the two generator of its top homology group. So this homology group with Z coefficients in degree n is isomorphic to Z, and this fundamental class here is one generator of Z plus or minus 1. And now I can change coefficients and look at this class inside the top homology group with R coefficients. So I keep the same notation because we will only use this class. So I send this map under this class under change of coefficients inside this group, and this is now my real fundamental class. So it's an element like this, like alpha in the nth homology group with R coefficients of M, and then I can compute its L1 norm. And this is what I will call the simplicial volume of M. So it's the L1 norm of its real fundamental class. Simplicial volume of M. So this can also be 0 as above or positive. Okay, so this was defined by Gromov. And let us compute a simple example to get an idea of what the simplicial volume is and what it measures. So let's do the simplest example we can think of for the one-dimensional closed-oriented connected manifold, the circle. So if we want to compute its simplicial volume, what we have to do is look for representatives of its fundamental class with real coefficients, take the L1 norm, and look for the infimum. So let's try to find such representatives. You have this circle. One way to represent its fundamental class is to take a triangulation of the circle in 3 simplices. Okay, I'll write Z for the corresponding cycle made here of 3 simplices, and below I will compute its L1 norm. Okay, so each simplex comes with the coefficient +1, so the L1 norm is 3. 1 + 1 + 1. Okay, but I can do better than this. I can take one simplex that goes once around my circle, and it also has coefficient +1, so its L1 norm is 1. Okay, if I was working with Z coefficients, I would have to stop here, but I have the freedom given by the R coefficients so that I can take one simplex that wraps twice around my circle. And now this does not represent this fundamental class, it represents it twice. But if I put the coefficient 1/2, then it represents this fundamental class. And its L1 norm is now 1/2. Okay, and now I guess you have seen what we can do. You can go as many times as you want around the circle. Say k times, you have to put the coefficient 1/k, then the L1 norm is 1/k. And now taking the infimum, as k goes to infinity, you see that the simplicial volume of the circle is 0. Is this computation clear? So yeah, don't hesitate to interrupt me in case. So this idea generalizes actually to any class of degree 1. Sorry, if you have a class of degree 1 in any topological space, you can always represent it by a cycle like this that you can represent by one simplex going k times around it. And so the same argument shows that for any 1 degree class, the L1 norm is 0. Okay, and there is an even more general result. It's a theorem that you can obtain by combining results of Trauber and Gromov. So it's also from the 80s. If the fundamental group of the manifold M is amenable, then the L1 norm is 0 for any class, not only in degree 1, but in all degrees, at least 1. In degree 0, no, because in degree 0, you have a bunch of points, and the L1 norm is just counting how many points you have. But from degree 1 and further, then the L1 norm vanishes. I'm not sure if you are familiar with the notion of amenable group, so let me give some examples. Finite groups are amenable, abelian groups, nilpotent, solvable. All these types of groups are amenable. groups that are not amenable, it's non-abelian free groups. These are not amenable. Non-abelian free groups are not amenable. Okay, so this invariant, the simplicial volume, the L1 norm, vanishes when the fundamental group is amenable. Okay, for now we have only seen vanishing results. So luckily for the theory, we have also not non-vanishing results. So here is another very important result of Minaev in 2000 that can be expressed as if pi1 of m, if m is a spherical, which means that the universal cover of M is contractible, and pi1 of M is what we call Gromov hyperbolic. Then the L1 norm of any class is bigger than 0 for every alpha non-zero. For every non-zero alpha in HK MR. And now we have to specify for every k at least 2. Okay, for k equals 1, we know that it's always 0. But in the case of Gromov hyperbolic fundamental group, for k at least 2, it's always positive. So for Gromov hyperbolic groups, if you are not familiar with it, think exactly of free groups. For, let's say, for n bigger or equal to 2, and fundamental groups of hyperbolic manifolds. These are some key examples of Gromov hyperbolic groups. They are very much studied in geometric group theory. So in order to make this result maybe a bit more geometric, I will state also another highlight theorem of the theory. This is due to Gromov and Thurston. They got it more or less independently. It's also from the 80s. And it's actually now it can be seen as a particular case of the theorem I stated above by Minet. That was a generalization. So this theorem here says if M of dimension n is a rented, closed, connected hyperbolic manifold, so it admits a hyperbolic metric, then the simplicial volume of M is the volume of M, the hyperbolic volume of M, up to a constant Vn that depends only on the dimension. Okay, so the simplicial volume is proportional to the hyperbolic volume. So I forgot to say when I define, excuse me, the L1 norm and the simplicial volume, that these things, are homotopy invariants. Okay, they depend on the homotopy type of the manifold. So they are topological invariants. But now you see here with this theorem that in the case of hyperbolic manifolds, this topological invariance actually is the same as this very geometric invariant, the volume. Okay, that's also why the simplicial volume is called simplicial volume. Okay, so this was L1 norm and simplicial volume. And this is a first result when you can see what kind of geometric implications the simplicial volume has. You can also remember that it makes a big difference between the amenable world and the Gromov hyperbolic world. And let me give you now some more results about this theory that motivated our work with Xi. So it's called Gromov's main inequality. And other results. So in the paper where Gromov defined this invariant and proved the theorem above, he also proved another one very important theorem that's called now main inequality. And it says the following: if Mn is a rented close connected Riemannian such that its Ricci curvature is bounded below by minus n minus 1. So any lower bound in some normalization, then the simplicial volume of M is less than or equal to n minus 1 to the n times n factorial times the volume of M in its Riemannian volume for this Riemannian metric we have on M. So this sort of statement is the model for all statements that come below. You have on this side something that depends on the dimension, something that is a geometric quantity, the volume, and it's bounded from below by the simplicial volume, so a topological quantity. So this is the importance of this topological invariant for geometry, that it's a lower bound for any Riemannian volume we can put on M. So actually, Gromov, this is a form in which we usually quote the main inequality, but he had it for every degree. So for every k at least 0, for every alpha in HKMR, he had the corresponding inequality that the L1 norm of alpha is bounded by is a lower bound for n minus 1 to the k factorial times the mass of the class alpha. And I'll define the mass in a few minutes. If you don't know what it is, think of it for now just as a generalization of the volume in lower degrees. Okay, so this is Gromov's statement. And this theorem gave rise to lots of works afterwards, because already Gromov knew that his constant here, it was not optimal. And he also thought that his condition here was not optimal. Actually, he conjectured that one could replace this condition on the Ricci curvature by a condition on the scalar curvature, so a lower bound on the scalar curvature of M. So these things gave rise to works in these two directions. On the one hand, improve the constant. On the other hand, relax the conditions. So I'll state a few more results that are improvements in one or the other directions. So the first one is by Besson, Courtois, and Gallo from 91. So the hypotheses are similar. Now they assume something a little bit stronger, that the sectional curvature of M is between -1 and 1. And then they get a better constant. So the simplicial volume of M is bounded above by n-1 to the n factorial over n to the n over 2 times the volume. Okay, so by this slightly stronger condition on the curvature, they improve a lot on the constant in this inequality. And in the other direction, the direction of relaxing the curvature assumption, there is a recent theorem by Braun and Sauer in 21. And last year, there was an improvement by Alpert, who obtains the same kind of result, but with a better constant using different methods. So the statement reads as follows. So for every V1 at least 0, for every dimension n in n, there exists a constant that depends only on this n and this V1, such that if we have M of dimension n, an oriented, closed, connected Riemannian manifold, with the condition that the volume of the balls of radius 1 around any point x of the universal cover are bounded by V1. So for every x in the universal cover, M tilde of M. Okay, so if M is a Riemannian manifold, so we can lift its metric to its universal cover. And if in this lifted metric, the volume of all balls of radius 1 are bounded above by some constant, some universal constant, V1, then we obtain a similar inequality. The simplicial volume of M is less than or equal to this constant and V1 times volume of M with its Riemannian metric. So same kind of statement, the simplicial volume is a lower bound for the volume up to a multiplicative constant. So now you could ask, what does this result have to do with Gromov's statement here? So apart from the fact that the statement looks similar, this condition here actually is very close. I mean, is close to a condition on the scalar curvature that Gromov wished for. So indeed, let me change the color if I manage. If you put an upper bound on the volume of balls, and if you do it not at radius 1, but at infinitesimally small radius epsilon, so in the infinitesimal regime, an upper bound on the volume of balls is equivalent to a lower bound on the scalar curvature. This you can see by taking the Taylor expansion of the scalar curvature at that point. And you will see that if you have an upper bound on the volume of small balls, then it gives you a lower bound on the scalar curvature. So if this result was not for radius 1, but for small radius, then it would have proven the conjecture of Gromov of his main inequality with assumption on the scalar curvature. Only it's not, we are not there yet. Here we really need balls of radius 1. The other relation between this result and Gromov's result is that actually you can obtain this result of Gromov with the Ricci curvature using this theorem. So this theorem implies the main inequality. Actually, not with the same constant. Okay, the constant will be worse, but it implies this statement for the Ricci curvature, because using the Bishop-Gromov inequality, if you are aware of it, you can show that having an upper bound on the volume of this one balls implies that the Ricci curvature is bounded from below. Excuse me, the other way around. If the Ricci curvature is bounded from below, you have an upper bound on the volume of balls, then you apply this theorem and you have Gromov's main inequality. Okay, so this is the relation between this result and Gromov's original result. And now I can state our result with Xi. If there are questions up to now? Okay. Sorry, let us change color. So our theorem says the following. Now the hypothesis is Mn is oriented, connected, but now not closed, complete suffices. It has a complete Riemannian matrix, so it's a oriented, connected, complete Riemannian manifold of dimension n. And we will need a quantity called the critical exponent that I will denote by delta. Then, for every alpha in H, K, M, R, for every K at least 1, the L1 norm of alpha is a lower bound for delta to the K times K factorial times K to the K over 2 times the mass of alpha. Okay, so now for a moment, I will try to split the screen, yes, so as to show you the two things at the same time. Here, so compare this statement with Gromov's and Besson-Courtois-Gallot's statement. So you see that the inequality that we have is of the same shape of this inequality of Gromov between the L1 norm and the mass. The constant is different. The constant looks much more like Besson-Courtois-Gallot's constant because it has this denominator here. So actually it's the same, only the degree has changed up to this delta. So this delta replaces the n minus 1 that we have in Besson-Courtois-Gallot's statement, and it makes it a priori better because Besson-Courtois-Gallot's constant depends only on the dimension. So all manifolds of the same dimension get this same constant. In our case, a priori, we could adapt the delta to each manifold. Okay, it's the critical exponent of this particular manifold. So it could get us better estimates. And indeed, n minus 1 is the worst delta that can arise under the hypothesis of Besson-Courtois-Gallot's theorem. Okay, so we have these two improvements. The one is that we get this inequality in all degrees with a better, slightly better constant. The other one is that we don't need the manifold to be closed. Complete is enough for us. And yeah, and so in dimension n, in the worst case, we recover exactly the inequality of Besson-Courtois-Gallot. So that's our statement. I think I want, yes. And one more thing, you notice that in our statement, there is no hypothesis about the curvature. In Gromov and Besson-Courtois-Gallot, there was an assumption about the Ricci or the sectional curvature of M. Here, we don't see any of this. Of course, it's not gone completely, but it's been replaced by this assumption on the critical exponent. So the curvature behavior of M is hidden in its critical exponent. All right. Are there questions? If not, I will repass to one screen. and go on. So now I owe you, I think, a few definitions. For example, the mass that I told you before I would define. So let me do that so that we know exactly what we're talking about. So we are in this setting. M is oriented, connected, complete, Riemann, and manifold. We take a homology class, and its mass is the supremum of the integrals along alpha of omega, where omega is any closed K differential form. Any, but not completely any, the comass of omega is bounded by 1. So this is the mass. So as I said before, it generalizes the volume. Put here a class of degree n, and here you will get the volume of your manifold. Now I have to tell you what this comass is actually. So for a differential form, the comass is simply the supremum over points of the manifold of the supremum of the value taken at this point by omega on some k unit tangent vectors. So the ui's are in the tangent space at P, and they are unit vectors. So this is a comass. And finally, to completely understand the statement, we need to know what the critical exponent is. So let me do it in general. Let's take a metric space X with a distance d. And let's fix a point x0 in X. Now, suppose you have a group gamma that acts on X by isometries. So in this situation, you can define the critical exponent of this action, of the action of gamma on X. And what is it? It's denoted by delta X gamma, and it's the infimum of the S in R, such that this sum S d x0 gamma x0 converges. So it's the smallest S that makes this converge. If S is very big, of course, this will be very small, and we look for the smallest. So it's non-negative real, and this is why it's called critical exponent. It's the exponent that makes this converge. And actually, there is a more geometric way to define it. Let me give it to you as well. Maybe you have seen this and not the other. So you can also define it in the following way. So suppose this is your space X, your metric space X, and you have x0 here, and you look at its orbit under the gamma action. These dots are gamma x0, the orbit. And now choose some radius r and look at the ball of radius r around x0 in your space X. And now count how many points of the orbit are there inside this ball, and take the logarithm of this. So in the right normalization, this looks like this. The number of gamma in gamma of such that the distance between x0 and gamma x0 is less than or equal to r. Okay, so the elements of the orbit that lie inside this ball of radius r. Okay, so this is another way to see this critical exponent. And you can check that it does not depend on the x0 you have fixed by triangle inequality. Okay, so this is a definition, and our delta, the delta that appears in our statement, this one, is the particular critical exponent that you obtain if you look at this situation. You have the universal cover of M tilde, and you know that pi1 of M acts on its universal cover by isometries. Sorry? Okay. And it's this delta you consider. So delta, the delta I wrote above is the delta M tilde pi1 of M. Okay. So this particular delta. So now we have all the definitions to understand properly the statement of the theorem. Oops. I show it again. Here. Okay. I would like, well, the time is going very fast, but so I will not be able to tell you many things about the proof, but I would like to make a few remarks on the result. So first of all, look at this critical exponent. You remark that if for the metric space X, you took the Cayley graph of a finitely generated group. So this has a natural metric, the word metric, and the critical exponent, so the group acts on its Cayley graph, and the critical exponent of this action, if you look at in this definition, is the lim sub of r tending to infinity, 1 over r log of the gammas. How many gammas make this distance smaller than r? Okay, so this distance, if you take x0 to be the unit in your group, this is actually, and you put d to be the word distance, the word metric. Here you are counting how many elements are in the ball of radius r in your Cayley graph. So actually this is what we call the exponential growth of the group gamma. Excuse me, the growth rate, the logarithmic growth rate of the group gamma. Okay, so this is the first remark. If X is the Cayley graph of gamma with some finite generating set, then delta X gamma is the logarithmic growth rate of gamma that you might know from geometric group theory. And then as a consequence, we have the following. If M, the manifold we are considering, was compact, then its fundamental group is finitely generated in particular. It's even finitely presented. Then we can look at its Cayley graph. And in the case that this fundamental group has what is called sub-exponential growth, okay, so this is an invariant of groups that says that the number of words in this generating set does not grow fast. This by definition means that this delta of the Cayley graph pi1 of M S of pi1 of M is 0. Okay, if it has sub-exponential growth, then this logarithmic growth rate is 0. And this implies that the delta in our statement, the delta of the action of the fundamental group on the universal cover is also 0, because the Cayley graph in this case for M compact the Cayley graph and the universal cover of M are quasi-isometric. Quasi-isometric. And the vanishing or non-vanishing of delta is an invariant of quasi-isometry. Okay, then delta is 0. And so what does our statement say when delta is 0? It says that the L1 norm of any class is 0 in all degrees at least 1. This is what we conclude from our theorem. Okay, and then compare this with what I told you at the very beginning, the result by Hauber and Gromov. Hauber and Gromov, where is that? Here, that if the fundamental group is amenable, then the L1 norm vanishes in all degrees at least 1. So actually, here we have recovered partially the Trauber-Gromov theorem. Because groups with sub-exponential growth are amenable. Okay, actually, we have to be careful. There exist groups that are amenable of exponential growth. And to this theorem does not apply. So we only partially recover the result of Trauber-Gromov for the group of sub-exponential growth, but already we have this. Okay, this was one remark. And the second remark, or the third one, is that in certain cases, our theorem can be improved to a two-sided inequality. So what do I mean? If M satisfies some more conditions, so it admits what we call a straightening, I will give you an idea what this is. A straightening and a uniform bound on the volume of the straight simplices. K simplices. Let's say CK at least 0. Okay. So okay, the straightening is something like this. In degree K, it transforms singular simplices into singular simplices, and straight simplices are in the image. Okay. The image of this straightening map, and this straightening, moreover, should be homotopic to the identity. Okay, so it induces the identity on homology. Okay, if M is such, then we get a double-sided inequality. Inequality of this form. 1 over this CK times the mass of alpha less than or equal than the L1 norm, less than or equal, here our statement, K over 2 mass of alpha. Okay, so in this case, the L1 norm and the mass of a homology class are comparable. Okay. And when does this happen? It happens for negatively curved manifolds. So for example, hyperbolic manifolds, they have a straightening. The straightening is looking at geodesic simplices. So if you have a very ugly singular simplex, delta k by sigma to this ugly simplex, you can transform it to make it straight by just taking the geodesic simplex that has the same vertices. Okay, this is the straightening simplex, and this indeed, you know that simplices in the hyperbolic space have uniformly bounded volume. So this is how it works. So this is one case, but actually there are more cases where the manifold is not completely negatively curved, but has what we can call sufficiently many negatively curved points. So the curvature is not negative everywhere, but in sufficiently many points it is. And then you have another kind of straightening, which is called the barycentric straightening. And this is due to my co-author Xi and Connell and Lafont. So in these cases, it's better than just one side inequality, but we have the two cases. Okay, so I have more or less 1 minute to give you a very quick idea of the proof. So what I will tell you is the main idea that is behind all three results. The Gromov original one, Besson-Courtois-Gallo, and our results all use a smoothing operator. What is this? The idea goes back to Gromov in this same article. So what is the idea? So in order to get good estimates on this L1 norm, what we need is to take some kind of average. So on a manifold, it's difficult to average because there is no way. But where we are able to average well is in vector spaces, or a bit less well in convex spaces, where we can take convex combinations of points. So the idea is to, instead of work in the manifold M, to replace the manifold M by a model of it that will be the probability measures on it. Okay, this is a convex space because convex combinations of probability measures are probability measures. And a very easy way to send points of the manifold to the probability measures is simply by taking every point to its Dirac measure. And so this is very easy and quite stupid, let's say. It's not completely stupid because it's pi1 of M equivariant. So if I move here by an element of pi1, it moves here accordingly my probability measure by the same element of pi1. So it's a model of M tilde inside the probability measures. Only this is really not continuous. There is a notion of a norm on the probability measures, and it's not continuous for this norm. It's very different. You have 2 points that are close here, and if they are not the same, then the two probability measures are completely different. There are one on one point and one on the other point, and 0 everywhere else, and so it has nothing. You cannot see the fact that the 2 points were close on this side. So the idea is, so the problem is that here it's not continuous. So the idea is to make it smooth even. So this is what the smoothing operator will be about. I will stop in 1 minute, excuse me. So a smoothing operator is a map S from M tilde to the probability measures of M tilde that is pi 1 of M equivariant and smooth. And so there is a precise definition of what the smooth should mean. And if you have such an operator, you can associate some norm to it. And then you have a theorem by Gromov that tells you that you can estimate the L1 norm in terms of this norm of the smoothing operator times the mass for every k at least 0. Okay, so which means that if you find a good smoothing operator, you will get good inequalities. And what we did in our work with Xi was to choose such a smoothing operator, compute its norm, and see that the inequality we got was the one I stated involving the critical exponent. Thank you very much for your attention. Sorry for being over time. I'll stop here.
Okay, let us thank our speakers. Anything else, comments?
Caterina, maybe I missed something, but
yes,
about this idea of the proof. Can you say something more about this pi1 equivariance? How do you make it pi1 equivariant?
yes. Let me try to. So is it clear that it's pi1 equivariant in the case of the Dirac operator? This will be something like gamma x or gamma inverse x. I'm not completely sure at the moment. So how do you make it pi1 equivalent? Well, you have to be able to define one such operator. So maybe what I can tell you is what our operator looks like. And you check that it is pi1 of M equivalent. And why is it useful that it's equivalent? Well, you are working here with a universal cover, but actually you are interested in your manifold downstairs, okay? For every alpha in HKM. So of course, if the things you defined are pi1 equivalent, then you can pass to the quotient and have a chance to say something about the quotient manifold M. So that's the main reason. So I can give you this concrete map, and there you can see that it's pi1 equivalent. So I'll quickly define it. So we do it in 2 steps. So we know we have to land in the probability measures of M tilde from M tilde. So we will pass through this L2 space. So take some measure on your M tilde that has something to do, let's say, with the volume measure on your manifold. So take a point in M tilde. There is a natural way to associate to it an L2 function. You can just measure some kind of distance between this point and other points. So you can take such a function, e to the minus s. S is a parameter. This is where the critical exponent comes into play. For s between delta over 2, delta plus 1 over 2, this function is L2. Okay, it converges. Now you want to make it a bit better than just L2. You want to make it norm 1 in L2. This is S infinity for the sphere, the norm 1 element. So you will normalize by the L2 norm of this. Okay, so now you have an L2 function, and this association here is pi1 of M equivariant. So if you move your point x by 1, you will move accordingly the function. Here, pi 1 of m acts here, we have said, but it also acts here by moving the argument. And this association is pi 1 of m equivariant. Now, how do you pass from a function to a probability measure? Well, this function, take any function f, as it will be of square norm 1, then this thing here, modifying your measure m tilde by f2 will be a probability measure. Okay, so you produce from an L2 function of norm 1, of square norm 1, a probability measure, and this thing is pi 1 m invariant. And then the composition is pi 1 of m equivariant. And thanks for asking, actually. So this is the smoothing we chose, and this one yields the inequality I told you.
So you choose the smoothing first and then define these things.
So we choose the smoothing. That is, we define this function. Take this composition. This is our smoothing. We call it SS. It depends on this parameter S. And now what we have to compute is the norm of this particular smoothing. If we compute this norm, then we get the inequality. And so the work is to come up with such a smoothing and then compute the norm and see what it tells us. And you see this S dependent on the delta, and by taking the limit when S goes to delta over 2, we get the constant that appeared in our statement.
Okay. Thank you.
Thank you for the question.
Okay, thank you. If you don't have any other questions, do you have any questions? Comments? No? Okay, let us thank our speaker again.
Thank you very much.
Thank you very much.